Great. All right. So, hello, everybody. So, I would like to thank you all for joining us today. And as you know, this is the second live session of our February theme, which is based on technology and artificial intelligence. And today we are so lucky to have Dr. Josiah Hanna with us for a live talk on development of autonomous robots. So before we start learning about this topic, I would like to introduce our structure to those who are new to our platform. So in the next half hour or so, Josiah will be telling us about how we can create robots that learn through interaction instead of being programmed to actually complete a task. And after this talk, which hopefully will last about 20 to 30 minutes, we will have a 10-minute comfort break where I will be collating all the questions that you have submitted to our social media accounts, to our emails, or to our YouTube channel chat function. So while Josiah is talking, please feel free to submit your questions through there. So during the break, what I will do is I will be collating all of these questions and I will be asking these questions on your behalf. So feel free to repost any follow-up questions if required. So before moving on to our discussion, I would like to briefly introduce Josiah too. So Josiah is a postdoctoral research associate who actually came here from US and who's currently based in School of Informatics at the University of Edinburgh. And in a few months' time, he's been so successful and he will be joining University of Wisconsin in US as an assistant professor, again in the Department of Computer Sciences. So as you may already read on our website, Josiah's research is focuses on artificial intelligence and machine learning, and he's basically aiming to develop algorithms that allow artificial intelligence agents such as robots to learn from experience rather than to learn from commands, if you like. So Josiah, again, thank you for joining us today. It's an absolute pleasure to have you with us, and we're all looking forward to hearing about your research in this field.
Thank you. Yeah, thank you for having me here. It's great to get to share this work. Okay, so I think my slides should be up now. Yeah, so thank you for the introduction. So today what I'm going to talk about is about how computers and robots can learn through interaction to solve tasks. So this is this work is part of the field of artificial intelligence, and within that machine learning work. And so the ultimate goal of my research is that computers and robots will be able to learn how to take actions to accomplish goals. So right now, everything that software can accomplish, if this is like an app running on your phone, or it's software controlling robots in a factory, someone has had to, in most cases, has had to kind of explicitly program how a certain functionality is going to be done. And so this approach really doesn't kind of scale to all the many different things that we might want computers and robots to accomplish. So the goal of my research is that instead of having to explicitly program things, computers and robots can try different actions. They can see the ones which lead to successfully accomplishing a task. And then they can repeat those actions. So all we need to do is be able to specify the desired outcome and let the software figure out how to take the actions which achieve that outcome. So if you want to, this area of AI is known as reinforcement learning. And to give you just like a general idea of what reinforcement learning is, you can think about how an animal learns to do a trick. So for instance, here I have, this is my dog Finley, and he's sitting after we've asked him to sit very nicely. And the way we got him to do this is that when he was sitting, we gave him a reward, so something that he finds like tasty, like a piece of food. And then over time, through that feedback, he learns that sitting produces this outcome which he wants, which is getting the treat. So we're not like having to say exactly this is how you sit, but we're just having to say this is the behavior that will give you give you the reward. And then that leads to the behavior being increased. So you can contrast this with how we might get a robot dog to sit, which is currently you would have to explicitly write a piece of software which causes the dog to move its joints in a way which produce the sitting behavior. So we have to know how to solve the task already, and then we can write software which accomplishes that. So the goal of the field of reinforcement learning is to develop algorithms that we can put into software to lead to either computers or robots figuring out how to achieve a desired outcome by just trying out different actions and seeing what works. So of course, besides just getting like robot dogs to do cute things like sitting like this, reinforcement learning can be used for a very broad number of applications. Any kind of to achieve any kind of behavior where we just want to be able to specify the desired outcomes and let software figure out how to actually achieve it on its own. So in the past 5 years, the area of reinforcement learning has seen a lot of kind of very notable successes on a variety of different applications in the real world. So some examples of this. So the company DeepMind in London about 5 or 6 years ago, they showed superhuman video game playing capabilities by a computer program. And this was done with reinforcement learning. A few years later, the same company also, they developed a program which could play the board game Go at a level that was better than any human, so able to beat human Go champions. This was really notable. Playing the game of Go at a superhuman level was considered a challenge for AI that wouldn't be solved for decades. As another example, here are some simulated robots playing a game of soccer. And these robots have learned to kick the ball, to run really fast, and a bunch of other skills. And they've learned to do that without being explicitly programmed how to do those skills really well. These successes of applying reinforcement learning have come in more game environments, but there's also a lot of companies are taking notice of this. So social media and web marketing, if you're scrolling through your social media feed and you're seeing advertisements which are like well-placed things that you're likely to click on, well, it's possible that reinforcement learning played a part in selecting what are the best advertisements to personalize to you, or what is the best content to show you at any moment in time. Google's begun using reinforcement learning as part of optimizing their data centers to kind of reduce energy cost, which is good for the environment as well as good for the finances of a company. And then as just one more example, control of home thermostat systems, where the thermostat needs to figure out how to adjust the temperature so that maybe it's not spending as much energy when you're not at home, but then at the moment that you get home, everything's a right temperature to keep you very comfortable. So reinforcement learning has like an enormous number of applications where we would like to be able to specify a desired outcome, but we want to let the computer figure out how to actually achieve that. And that's really exciting because it's possible that human intuition for how to accomplish a certain task may be it may not be the best possible way to do it. We may not be able to tell a computer exactly how to solve something, particularly difficult things like a robot controlling its body to walk really quickly. But with reinforcement learning, that can just be kind of automatically figured out. So I'm going to next kind of give just like a high-level introduction to how we what a reinforcement learning algorithm, how it models the world, and what are the challenges that have to be overcome. And then I'm going to talk more about how we can actually do this on physical robots. So it's just a motivating example to describe a particular type of problem that can be modeled and solved with reinforcement learning. Let's imagine that we have a robot that we want to learn to play soccer. This image is taken from, there's an annual RoboCup competition where people are working on like how can you develop robots that can play soccer at superhuman capabilities. with the goal being that this drives a lot of research on basic robotics and learning research. So at any moment in time, our robot that we want to learn is going to be it's acting in the world. It's in the presence of other robots that may help it or may try to prevent it from achieving its goals. There's objects like the ball and the goalpost, and it has an objective, which is it just needs to get the ball into the goal. So this would be like it is a very difficult task to try to like program exactly how to play soccer. But it is very clear. There's like a very clear objective here, which is just to put the ball in the goal. So it's easy to tell when you're doing the right thing, even if we don't exactly know how to do that or how to program that. So at any moment in time, we can say that there's a certain state of the world. So maybe like where the other robots are, where the ball is, and where the robot that the software is running is in the world. And we also have feedback in the form of a goal. When the ball is in the goal, then that's positive feedback, and otherwise there's kind of no feedback occurring. And then the robot has available to it different actions it can take. So how it can control its legs to walk or to kick the ball or to do other things. So what we want to do in reinforcement learning is we want to have some type of decision-making function which can tell us how to map states of the world and feedback into actions to take, so as to kind of maximize the amount of positive feedback that's received. And it's not important to exactly understand how this decision-making functionality is implemented. In recent years, a really popular approach is to use a model called a artificial neural network, which is somewhat inspired by human neural networks in the brain. But really what it is a mathematical model which maps some type of input to some output, and you can change different weights in this model to change what that input to output mapping is. So in our case, we just want a mapping from states to actions. And so neural networks are frequently used for that. So in reinforcement learning, what we ultimately care about is how can we change, or how can we learn this decision-making functionality such that our state to action mapping is going to increase the amount of positive feedback which is received over time. So this is a sequential process. So after an action is taken in the real world, the state of the world will change as a function of that action, and then the next, and so then another action has to be taken, and this can kind of continue indefinitely, or until you've decided that the task is done, and so on. So this is that's like a high level idea of the problem that has to get solved in reinforcement learning. There's several different, to be able to successfully do this, to develop a computer algorithm which can learn this state to action mapping to maximize feedback. There's several kind of key research challenges which have to be dealt with. So what these are is the first one is you have to be able to tie long-term effects back to the actions that caused them. So you can imagine that if the robot kicks the ball from very far away from the goal, it's going to take a little bit of time for the ball to travel and then arrive at the goal. So it may be like several seconds later that the feedback of the goal being scored from the robot kicking the ball is actually received. And maybe there's like lots of other things happening in the world at the same time that the robot kicks the ball. So how can it actually learn over time that it's the action of kicking the ball which is what causes the feedback to be received? So this problem is known as credit assignment in reinforcement learning. So it's really a kind of a key challenge. Like, how do you know what are the actions which led to the feedback, particularly when that that feedback happens in like a delayed timescale. Another key challenge that has to be dealt with to build a reinforcement learning algorithm is the ability to explore new actions, but then also decide when to stop exploring, like when what you've done is good enough, and you don't need to try out new actions because trying new things may kind of hinder your ability to exploit the best actions that you've seen so far. This problem is known as the exploration versus exploitation trade-off. It's a very difficult problem. In fact, during World War II, Allied scientists considered this problem so difficult that they thought about dropping it on the Germans so that their scientists would waste all of their time trying to solve it as well. The final, a final key problem to mention here is that reinforcement learning agents have to be able to generalize what they've learned across different situations. So, in our robot trying to learn to play soccer, there's a lot of different situations might come up, a lot of different world states that it will encounter. We don't want it to have to try out every possible action in every possible state to know what the best actions to take are. So it needs to be able to just try out things in some small number of the states, but then generalize what it's learned to new ones that it hasn't encountered. And this generalization capability, there's been a lot of recent advances in AI and how to generalize across unseen instances of things, and that's really driven a lot of the success in reinforcement learning as well. So there's been decades of research addressing these three challenges, as well as other challenges that come up in reinforcement learning. And that's led to a lot of really well-performing algorithms, and people are beginning to put this into a variety of software. And so that's led to a lot of these really recent empirical successes, as well as applications in industry. However, there's still a really important limitation here, which is going to hinder the ability to apply reinforcement learning to things like physical robots, as well as maybe applications like healthcare or just anything where you can't spend a lot of time learning. So if you look at this, say, superhuman performance in video game playing, if you look a bit closer at the result, you see that it took a couple of weeks and the computer had to try out 50 million actions before it found actions which led to being able to play a single game really well. Similarly, this game of Go, the computer played weeks of millions and millions of games upon itself using like an enormous amount of compute power to be able to master the game of Go. And as just one more example, these simulated robots took 1.5 years of compute time to learn all of the skills needed to play soccer. So I think a big question which is being asked then is, can reinforcement learning algorithms actually be data efficient enough for real world applications? Meaning, like, are we going to have to, if we try to apply reinforcement learning to some new task, will it be able to learn in like a reasonable amount of time? So an important thing to point out with some of these successes which have happened is that they're happening in virtual worlds or simulated environments, such as games. And in these type of environments, it's possible to maybe like run the algorithms in parallel so that you can collect experience much faster. So for instance, with like simulated robots, they could you could have hundreds or thousands of robots all learning at the same time and sharing what they've learned. So kind of a key question for scaling reinforcement learning to new challenges is, can computers and robots learn in virtual worlds or simulations, and what they learn actually transfer to the real world? So tackling this problem, I think, gives us a really powerful tool for being able to use reinforcement learning on like a much broader set of real world problems. And so it's a main thrust of the research that I've been doing. So just to kind of motivate this a bit more, so this is some experience that I had during my PhD working on simulated robot soccer. You can see that the robots in this video, they're moving fairly quickly. They're able to kick the ball over long distances, and they're like coordinating well together as well. And so a big part of that is that their skills are heavily optimized using reinforcement learning algorithms. So there's some important advantages to being able to do all of this in simulation. Within simulation, you can have hundreds or thousands of robots trying out the same different skills at the same time. So this greatly speeds up the time to learn. Similarly, you don't have to worry about your robots breaking or wearing out because they're just simulated. If your robot falls over as it's trying out some new way to walk, it doesn't matter. You can just kind of restart it standing back upright. And so, if you could just like learn in this type of setting, you can like potentially learn much quicker than otherwise. So this contrasts pretty heavily with what you would see if you were trying to do things on physical robots. So here's some robots playing soccer in the physical world. You can see they're moving slower. They kick the ball less accurately and less far, and just otherwise, like it's not quite it's not quite the same level of ability that's seen on the simulated robots. And that's because everything on the physical robots is pretty much hand tuned. Someone has to explicitly program how to walk, how to kick the ball. And doing reinforcement learning isn't really an option because we're limited to just a handful of robots, not hundreds or thousands, but maybe 1 to 5. And if the robot falls over when it's trying out a new skill, there's a real possibility it would break. And then you're completely done with learning. Or even over time, the robots, they kind of wear out and then don't work as well as they did initially. So we really have to be able to learn like much quicker. So, one possibility would be that we just do the learning in the simulated environment and get it to transfer onto the physical robot. So, we can start with let's say we want to get the robot to learn to walk really quickly. Might start with the robot walking kind of slowly in the simulated environment. We could have a similar walking behavior on the physical robot. We then apply reinforcement learning entirely in simulation. As shown here on the top right, you end up with a much faster robot walking. But then, unfortunately, if you just take this directly optimized skill and try to put it onto the physical robot, you have to stay really close because kind of inevitably what you learned in simulation will fail to transfer into the physical world. And that's just because inevitably the simulation is going to get some things wrong about how it's modeling the real world. So for instance, maybe it thinks the ground is really smooth compared to the carpet that the physical robot actually walks on. And so, when this happens, the robot may learn that it can just slide its feet along the ground to walk really quickly, but this doesn't work when you actually try to deploy it on the real world. So it's often noted for people working in robotics that things that work in simulation often don't work when you try to take them into the physical world. But we still really would like to be able to use simulation because it has the potential to make reinforcement learning work in the real world much better. So towards actually leveraging simulation for real robot reinforcement learning, we use an approach that gradually improves the simulation over time so that it's a better model of the real world. And then we can hope that reinforcement learning applied in simulation will actually lead to real world improvement. So we use a framework called grounded simulation learning that was previously introduced by some people that I collaborated with at UT Austin. So in this framework, we have a robot which is kind of initially moving in the real world and trying different actions. We can record data about what the effects of these actions are while the robot's acting. And then we can modify the simulation so that the simulator produces data which better matches what we're observing in the real world. Once we've modified the simulator, we have a more realistic simulator in which we apply reinforcement learning. And then because the simulator's been more realistic, the trained robot skill which comes out of that, we can expect to improve performance on the physical robot. And this can be an iterative process where the simulation is kind of continuously improving so that the robot's like building up a better model of the world and while simultaneously learning how to accomplish a task in it. So the key question in this research then is how do we make a simulator more realistic? So if you think of the type of interaction that that we're trying to model here, we have, there's the state of the robot is being looked at by some decision-making function, which is telling an action, which is then sent to the robot, which will cause a change in the state. And this process kind of would like loop forever as long as the agent is, as long as the robot is acting at its task. So if we want to make the simulation more realistic, what we want to see change is that sometime from when the action is sent to the simulation and a new state is encountered, we want that new state which is encountered to be more like what would happen in the real world. So we want the state of the world to change in a way which is similar to what we want the state of the world in the simulation to change in a way which is more similar to how it would change in the real world. So from the decision-making function's point of view, at some point from when it sends its action to the simulation and gets a new state back, something needs to change. And so what we do is we change the action that gets passed into the simulation to, in effect, produce a different effect, but one which better matches what would happen in the real world. So we do this by adding, after the action is taken and given to the simulator, we add what we call a grounding module, which just modifies the action being passed in the simulator. This grounding module can be learned with machine learning using just a small amount of data collected in the real world. So we're not having to kind of like, we're not shifting the burden from programming the behavior to programming the simulator, but instead we're going to use machine learning to kind of learn a better simulator. This grounding module just has two components. The first is we learn how to predict what the effect of an action would have been had it been taken in the real world. And then we also predict what action would cause the same effect to happen in simulation. So we can just learn this completely with data observed by when the robot acts. And so then to produce data for the reinforcement learning agent to learn from, we have the same like decision-making function producing actions, but we then modify the action before it's passed to the simulated robot. And this makes the states which the decision-making function is encountering more similar to what would be encountered in the real world. So if our simulation now better matches the real world, we can just apply a reinforcement learning algorithm there and learn like a new behavior for our robot completely in simulation, and then hope that it will actually transfer onto the physical robot. So I'm going to show it just a demonstration of this technique working in practice. So the task that we're interested in learning is we want to learn a fast walk on this bipedal robot called the Now robot. We're going to learn from we're going to have this robot walk in the physical world up and down a soccer field for 5 minutes. And that's going to collect enough real world data for us to effectively ground the simulator to make it better match the real world. And then we're going to employ a reinforcement learning algorithm, which is going to require about 5,000 minutes of walking. So orders of magnitude more than we could possibly hope to collect on the physical robot. And we're going to learn a faster walk by doing this. So I'm going to show some videos now. Our starting point for this is a hand-coded walk, which was developed for robot soccer on the Now robot. This walk has been used by a number of championship teams there. So it's one of the fastest ones that we know. It's the fastest walk that we know of for this robot, but completely hand-tuned. This is the same walk in the ungrounded simulation before it's modified. That actually went a little fast. Let me skip back a second. So this is now in the unmodified simulator, the robot walks much more smoothly than we would see in the real world. So that's a difficulty for learning to transfer well. Once we've grounded the simulation, the robot's going to move more like it did in the physical world. See, it's just like a bit rougher, as if it's like dealing with the carpet. And then, so after we apply reinforcement learning in the grounded simulation, the robots learn to walk over 40% faster than where we started, which was already a state-of-the-art walk for this robot. So we've learned without having to explicitly program this robot, we've learned a much faster walk just by applying reinforcement learning in simulation. So with that, I'm going to now conclude the talk. The things that I'd want you to be able to take away from this is that reinforcement learning is a really promising approach to allow computers and robots to improve over time by learning from interaction. All it takes is being able to kind of measure, what the desired outcome is for a certain task, and you don't necessarily need to explicitly program how to accomplish something. Just a reinforcement learning algorithm allows the computers or robots to figure that out for themselves. Current reinforcement learning algorithms have been developed, and they're beginning to see tremendous successes applied to a wide number of tasks, but they still require lots of experience to be able to solve tasks, and that makes them difficult to apply for things like robotics, self-driving cars, healthcare, other situations that we might want a computer to be making more decisions, but we don't know exactly how to program the way to make those decisions. Learning and simulation is a powerful approach to accomplishing this goal. If we could just simulate environments of interest and apply reinforcement learning in those, then learning can be done much more efficiently, and it would really make reinforcement learning more broadly applicable to problems in the real world. However, just kind of naively learning in simulation often doesn't work, and because reinforcement learning will find inaccuracy in the simulation and exploit that, and then what it learns won't transfer to the physical world. So this is the focus of my research, and the algorithms that we're introducing there is to be able to leverage simulation to support reinforcement learning. Just real quick, I want to acknowledge some collaborators. The work that I talked about was done at the University of Texas at Austin before I came to the University of Edinburgh. So this was work done with my PhD advisor, Peter Stone, as well as Siddharth Desai, Haresh Karnan, Ishan Duragar, and Garrett Warnell. And with that, thank you all for your attention watching the talk, and I'll now be happy to take questions.
Lovely. Thanks very much for this interesting talk, Josiah. So now we're going to give a break for 10 minutes, and then we will resume at 12. So hello, everyone. Thanks for staying with us during the break. Now it's time to get answers to your questions. So Josiah, again, thank you very much for this interesting talk, and you can tell that people were interested, and we can measure it from the number of questions that we have actually received. So I'm going to start with one of the questions. So I'm going to read them from my phone, if that's all right with you.
Yeah.
And I'm going to start with the question that we had from one of our audiences. So can you tell us a bit more about how do you actually create this simulated world for robots to learn in the first place? And how challenging is this as a method?
Yeah, so the first thing I'd like to say on that is that one of the great things about simulation is that there's already lots of existing physics simulations available for robotics. So there's lots of people interested in how do you simulate physical processes. There's the video game industry. So like lots of people are interested in how we can like build these really accurate models of the real world. So that gives us like an off-the-shelf tool right away, which is and that's what we're hoping to be able to leverage for reinforcement learning. Now, it's also is like a very interesting question of how you can build these models from scratch. Like, so for instance, maybe the robot doesn't have a simulator or any type of model of the world available to it already. And so we just want it to be able to like interact in the world and build up some type of like model of what happens when it takes certain actions. So there's this area of model-based reinforcement learning that does look, exactly at this question of like how such a model could be built from scratch. It can be very challenging depending on the task. There's some task where building an accurate model of the way the world changes can be very difficult. And there's areas of reinforcement learning that look at how you can, better solve tasks without ever having to learn an explicit model too.
Okay, so in comparison to, let's say, in 10 years ago or 20 years ago, in comparison to those methods, what are the differences and how do you think these are more advantages than those?
Yeah, so looking at, I guess is the question more about reinforcement learning methods, how they've changed over, say, the past 10 years. So the where a lot of improvement has come in the algorithms is the ability to generalize across new situations. And this isn't necessarily so much of a breakthrough in the fundamental reinforcement learning capabilities, but that there's been tremendous advances in the use of artificial deep neural networks, which are very capable of they do a good job of generalizing across different possible inputs. So maybe like, you see an image of a dog looking one way or an image of a dog looking a different way, and it still, can recognize that it's the same dog. So the generalization capabilities that artificial neural networks have brought in have enabled reinforcement learning algorithms, which use these networks to generalize much better across different situations.
All right, great, thank you. That's very interesting. So, obviously, anyone who's into films or who's been watching lots of sci-fi coming from 1980s onwards, we've always been sort of imagining about robots taking over either our lives or being such a big facilitators or even being friends with us, actually. So, what do you see as the future of robots with this acquired learning? Do you think we're going to reach to the level that has been anticipated in these sci-fi sort of movies? And what do you see is their potential for use in society?
Yeah, so I guess I'd say that it's not something that really keeps me up at night about this kind of sci-fi possibility. I think with robots, it's still enormously difficult to get things working in the physical world. I think we see these big successes like a computer beating a human at the game of Go, and think, well, Go's really hard, so like a robot walking across the room and picking up an object must be easy. But we really kind of find that it's much more difficult to program these kind of like physical skills and like learn these physical skills. So I think we still have a ways to go there. I think with this kind of learning, there are potential downsides that many people are working on with societal impacts. Like, so for instance, just to one of these would be like, well, we have to be able to specify to the computer what it means to accomplish a task, and that needs to be done in a way which aligns with our human values. So for instance, maybe you want like a more subjective experience, like we want to maximize user enjoyment on social media, and apply reinforcement learning to do that, but you give it an objective like maximize the number of times they like an image, and you end up just showing the person clickbait type thing. So how do you give the computer an outcome it can optimize, but that aligns with human values? That's like one example of maybe a more pressing concern with the development of these algorithms.
And I guess the real challenge will come, obviously the norms or ethical values or generally the common sense will change between different backgrounds as well, or it can even change from, let's say, Manchester to Edinburgh. One thing that's acceptable up there might not be down here, or vice versa. So I suppose there will be a lot of challenges in that sense. So how do you think, realistically speaking, these technologies will actually be able to overcome or be able to sort of reach to that level of complexity, or are we just asking too much? Do you think we will see it within our lifetime?
Yeah, so this question of value alignment it's a bit outside of like the area that I directly work on. I think it's a challenging problem, and I know there's like great people working on it. So, but I'm not sure I could put a time frame on how soon it could be solved. And maybe there's something like as you point out, there's can be like tremendous variation between even like different cities. So if you're developing software which is more localized, to try to take into account localities, or maybe even just like certain communities, what their values are, then that can help things progress further along. I do think it's important though to keep in mind that particularly with a lot of these technologies being developed by like people with like computer science degrees who went to like strong research universities to try to to take into account the values of the people that are using the technology, and not just like maybe force on what you particularly find is like the right values the technology should have.
Okay. All right, great, thank you. So the next question is, firstly, the audience is thanking you for this interesting talk. So what is the most common area or industry that reinforcement learning being utilized, and where do you reckon it will years to come?
Yeah, so it's reinforcement learning is being used by a lot of like internet companies. So applying reinforcement learning on the web there's some nice advantages. You have like maybe millions of users. So you've got these problems that I'm talking about with like how do you collect data, enough data to learn from, is you don't have that problem as much. I think where I'm really excited for its application is robotics, and it's just like very hard to kind of explicitly program robots to do to make certain produce certain behaviors. So I'm excited for the being able to use reinforcement learning there. Yeah.
Okay. All right. Great. So, how far do you think we are from having robots doing daily tasks for us? Do you think it's something that we will be able to walk into a Boots or Sainsbury's and buy it and get it to do our daily chores?
Really not sure, and it's hard to predict these things. And you can get lots of, I think there's high variance on even among AI experts about when when these we'll start seeing these applications of physical robots. I think to the when you're able to form a controlled environment for a robot, then there's just like a more predictable environment, maybe less human interaction, which can be like hard to predict. Then there will be like those are like environments where robots will be like increasingly better able to be deployed. I think there's like a lot of interest in self-driving vehicles right now, because roadways are relatively more controlled than just trying to walk through Sainsbury's or something.
Okay, all right. Thank you for that. So our last question is about your research interests. So, oh, sorry, second to last. So, what is your next research goal?
Yeah, so the one project I'm very interested in is kind of continuing in this using simulation vein, but I think so. One limitation with kind of current approaches to leveraging simulation is that simulators are trying to model like every little detail of the world right, and that's not really necessarily what you need for effective learning. Like what you care about is modeling like relevant task details well. So and there's even like an analogy to how we like think about the world. Like if I think about going into the kitchen and like making a cup of tea, it's not really that important that I know what pictures are on the wall and stuff like that, or where other things in the kitchen are. So I'm very interested in how the ideas of like abstraction, like abstracting away unnecessary details, decomposing tasks into hierarchies, and also like leveraging simulations, how all these ideas can play together.
Okay, great, lovely, thank you. So our last question. So what sensors do your football robots have that are used to train the model that adapts the simulation to real world?
Yeah, so we're relying on proprioceptive information, like so what their current like position of their joints are at any moment in time. So basically, just measuring the angle that say their arms or legs are, and then they control their arms and legs by like setting a desired position to move their joints to. So we're building a model of how the robot's joints are moving as a function of the desired angle that the robot's trying to move them to.
Okay, all right, lovely. I'm just checking quickly if we have got any other follow-up questions submitted. I think we're good. Well, thank you very much. It has been an absolute pleasure to have you on board and to actually listen
Thank you
to the
for having me.
research that
Yes,
you're
thank you.
doing.
It's very fun.
Yeah, great. Thank you very much. And everyone, so this is our last live session for February. We will be releasing our hands-on activity in a week's time. And in addition to that, please keep watching the space for the theme that we're going to have for March and for our anniversary month in April. So thanks very much for your attention. See you next time.